is where the station was built, on the bank of the Severn estuary, midway between Gloucester and Bristol. The soil here will support the massive weight of the structure and plant, and there's plenty of cooling water nearby. The net output of the station is 275 megawatts, using natural uranium in the two gas-cooled, graphite-moderated reactors which we see here in this model. The central area contains the two reactors and a cooling pond, together with various buildings for fuel storage, decontamination and waste disposal. The reactor buildings accommodate control systems and various services. 4 monotower cranes were used for the construction of the pressure vessels and structural steelwork. The 2 blower houses on each reactor are associated with 8 boilers. In all, 16 boilers supply superheated steam to the turbo generators in the turbine hall, which, together with the pump house, is situated outside the reactor area. Over here in the model is the cooling water system. 2 tunnels carry the water from an intake to the pump house, which delivers it to the condensers in the turbine hall and back into the River Severn through an outfall. A baffle wall prevents the warm water at the outfall from being recirculated through the intakes. Berkeley is the culmination of many years of intensive research and development in the nuclear field. Within the group, engineers, physicists and mathematicians are engaged in the design of nuclear power stations. Berkeley is one of the first. Construction work began in January 1957. Within a matter of hours, machines were stripping the topsoil from the excavation areas. With more plant and supplies rolling in daily, the 96-acre site was soon a going concern. Excavating the reactor foundations was a considerable earth-moving job, digging out 80,000 cubic yards of earth to form 2 pits 30 feet deep, 350 feet across. The excavations were kept dry by lowering the ground water level with a system of deep water pumping. Submersible pumps were inserted in the ring of wells surrounding each excavation. The turbine hall was the biggest excavation on the site, 550 feet long, 40 feet down. 100,000 cubic yards of earth out of this one. At this stage, pipes were laid for the duct which carries the power cables from the turbine hall to the switchgear site. By the summer of 1957, the batching plant was all set to start concreting the foundations and biological shield on the first reactor. The concrete was pumped through pipeline direct to the job. The main concrete raft on each reactor is strong enough to bear a load of 50,000 tons. The 8 boilers and the 2 blower houses are carried on an annular raft round each reactor. Work was well ahead too on the turbine hall foundations, turbo blocks and cooling water duct installations. The deepest excavation on the site, the pump house, 70 feet down because the pumps are fed by gravity and have to be below the level of low tide. Meanwhile, a Bailey bridge was constructed for access to the intake cofferdams in the river. Excavation work on the tunnels to the pump house had also begun. These go down to 100 feet below ground level. Over here at the outfall, piles are being driven for a cofferdam. To ensure water at all stages of the tide, a wide channel was dredged in front of the water intakes. Marine surveys were carried out to determine where to dredge, and later to make sure that there was no serious silting of the channel. The dredging was carried out in a patterned form, so that it would prove self-scouring. Back to the reactors again. They're up to lift 4 on number 1. This is the cooling air duct for the thermal shield being placed in position. By the autumn of 1957, the foundations on the first reactor were ready for the construction of the pressure vessel and biological shield. The pressure vessel is a dome-ended cylinder, 80 feet high, 50 feet in diameter, built of 3-inch steel plates welded together. Inside is the graphite core. Round the pressure vessel is the double-walled thermal shielding with a 2-inch air gap. Surrounding this, the concrete biological shield, 8.5 feet thick at the sides, 10.5 feet thick at the top. Shaping the plates of the pressure vessel at Wolverhampton called for extreme accuracy to ensure perfect welding. Special dies were used for the dome plates, which have a sharper radius in one plane. After shaping, the plates were prepared for welding by a special flame planing technique which produces the correct weld preparation angles on the curved edges. An accuracy test for the plates on the lower dome of the pressure vessel was made on a test rig before sending them to Berkeley. The dome, of course, is inverted here for easier inspection. To speed up construction on the first reactor, the lower dome was assembled and welded on a special site nearby before moving it into its final position on the raft. On the second reactor, however, there was plenty of time to construct the whole vessel in position from the beginning. A picked team of welders went through a course of instruction on the site to ensure the high quality of work required. All welding was to Lloyd's Class 1 standard, and every inch of every weld was scrutinized by X-ray. The plates of the dome were welded in a heated, weatherproof enclosure on the assembly site. The foundations are nearly ready to receive the dome. Looking down, we can see the ducts for the 8 gas inlets which penetrate the biological shield to enter the dome. Here, thick, reinforced concrete secondary shielding was constructed round the pressure vessel and parts of the ducting liable to become irradiated. Meanwhile, the thermal shield was erected to 2/3 of its circumference to allow room to move the dome in on rail tracks. The dome is supported on its plinth by specially designed A-frames to take up thermal movement, 18 in all. With the lower dome in position, the gap in the thermal shield was now closed. Here, below the dome, the 8 gas inlets are being welded in position. Above the dome, at the base of the pressure vessel, the diagrid structure which supports the graphite core is being installed. The 2 monotower cranes on the first reactor are now in operation. This method of construction, calling for close coordination between civil and mechanical engineers, cuts out heavy lifts. The cranes can tackle loads up to 15 tons. Covering all construction requirements for the job. Construction of the pressure vessel and biological shield proceeded simultaneously to a carefully worked out plan. Special techniques were used in the placing and compaction of the concrete to produce an exceptionally high quality. All materials were rigidly controlled by laboratories on the site and samples taken from every 200 cubic yards of concrete placed. During the construction of the pressure vessel, a removable roof was used so that the plates could be lowered inside for welding. After the plates had been lowered into position, the roof was replaced on each occasion. Strict temperature control was of vital importance in welding these plates, and the roof provided the necessary conditions under which the assembly crews and welders could work most efficiently. We'll leave the reactors now and have a look at progress on the river works. Offshore, piling was in progress on the baffle wall. This is a sheet steel box-piled structure 1/4 mile long. It separates the comparatively warm outfall water from the cool water entering through the intake. At the intake, construction work on the 2 tunnels was well up to schedule. The tunnels are 1,000 feet long and are faced with precast segments with a concrete lining. These tunnels will supply 21 million gallons of cooling water an hour to the station. Good progress had been made too at the outfall works and on the installation of the cooling water ducts. After passing through the condensers in the turbine hall, the cooling water is discharged back into the river through 4 culverts, 1 for each turbo alternator. They're nearly at the top now on the first reactor. The surrounding reactor building has been rising with the biological shield. Inside, at the top, we can see where the 8 gas outlets penetrate the biological and thermal shields to enter the pressure vessel. This is one of the apertures which have been cut in the thermal shield to accommodate the gas ducts. The sides of the biological shield and pressure vessel have now been completed. In order to construct the upper dome of the vessel, a steel template was placed on top to support the dome plates for welding. With the last plates of the top dome in position and welded, the girders for the pile cap were erected. Above is the charge face for loading and unloading the fuel elements and the boron steel control rods. This is where they will go, from the charge face, down through the pile cap, through the apertures in the top dome, into the graphite core. The steel framework of the blower houses and steam mains gallery has now been erected round the sides of the reactor. We'll have a look at the boilers next. There are 16 of them for the 2 reactors. The boilers are 70 feet long and consist of 5 cylindrical sections with a domed section top and bottom, all welded together to Class 1 standards. Before erection, each vessel was stress-relieved by induction heating and pressure tested to 180 pounds per square inch. After testing, the boilers were moved on bogies to their erection position at the reactor and raised with gin poles and 2 30-ton electric winches. The steelwork has been erected round this boiler, and before it is clad, we can see the high and low pressure steam drums. The superheated steam is delivered to the turbo alternators at 320 and 76 pounds per square inch. These are the banks of tubes through which the water will circulate inside each boiler. Some of the boilers have already been clad, and on top we can see the temporary structures containing the clean conditions room for installing the tubing. Men and materials were checked here for absolute cleanliness before entry. This is one of the tube banks being lowered into the boiler from the clean conditions room. The steelwork for the bridges connecting the boilers to the reactor has now been erected. And over here are the pipes which lead down into the trench, which will carry the superheated steam from the boilers to the turbine hall. This is one of the 9 flexible units used in each gas ducting circuit connecting the pressure vessel to the boilers. They're really hinges which allow the thermal movement between boilers and pressure vessel to take place freely. Here's one of the units in position. By the spring of 1959, good progress had been made on all projects on the site. Reactor number 1 well advanced, number 2 close behind. Offshore at the intake, the tunnels were nearing completion. In addition to the 2 main intake tunnels, a third smaller access tunnel had also been constructed. Concreting work on the outfall too was well advanced, and over at the pump house, the pumps which deliver the cooling water to the 12 condensers in the turbine hall were being installed. The 4 turbo alternators were constructed at Manchester. They're 3,000 revolutions per minute machines designed to accept steam at 2 pressures generated by the boilers. The alternators are hydrogen cooled and generate at 11,800 volts. After assembly and testing, the turbo alternators were installed on the concrete turbo blocks which form part of the turbine hall foundations. There are 3 condenser shells on each turbo alternator. Some of the condensers have already been installed. This one is in process of being tubed. The turbo alternators feed 6 transformers. Here's one being assembled. After testing, it is ready for its journey by road to Berkeley. On arrival, the 6 transformers, comprising 2 station and 4 generator transformers, were installed here alongside the turbine hall. During 1959, good progress had been made on both reactors. Work on the central cooling pond was well advanced. Roofing nearly completed. In the first reactor, the pressure vessel has been stress relieved by electric induction heating and pneumatically pressure tested to 211 pounds per square inch. Here, underneath the lower dome, is the cooling air duct. The cooling air from the duct circulates round the thermal shield. After being filtered, it is discharged into the atmosphere. We're above the pressure vessel now. The pile cap is being concreted. The central area contains the charge, discharge and control rod standpipes. The shutter tubes round these were welded into position and extended with each lift as concreting proceeded. A 7-inch layer of iron-shot concrete was used to increase the density of the pile cap to the value required for radiation shielding. Everything is now ready for placing the graphite core inside the pressure vessel. The core consists of vertical columns built up from blocks of graphite machined to an accuracy of 5/1000th of an inch. Each column is 30 feet high and is individually supported through a ball bearing assembly on the dia grid. This transmits the weight of the structure to the 18 A-frames under the pressure vessel. The completed core contains over 3,000 fuel and control rod channels. The control rods are manufactured from stainless steel containing 4.25% boron. There are 132 in each reactor. The rods are raised and lowered into the graphite core as required by synchronous motors. One or two of the fuel elements, there are over 42,000 in each reactor, one or two may fail in use, and special equipment had to be designed to detect and locate the suspect or burst cartridges in time to remove them before any significant contamination developed in the coolant circuit. This is the equipment being prepared in a London factory for dispatch to Berkeley. Inside the reactor, the detection tube banks are placed in position over the graphite core. In operation, samples of the cooling gas are drawn away through the tubes from each fuel element channel. Contamination in any channel is immediately located in the control room. To record the temperature of the graphite and fuel elements, over 1,000 thermocouple cables are used in each reactor. Throughout Berkeley, more than 430 miles of instrumentation and other cable have been installed for power control and station services, running at 2,900 revolutions per minute. Test rigs were extensively used to prove special features of the design. 1961. 4 years of construction have ended. Commissioning engineers and physicists take over. A 3-month series of stringent tests on the first reactor and its associated equipment begins. First, the 8 blowers were started up and run at full speed. Pressure tests were then made on the gas circuits and pressure vessel. To check and confirm the volume of gas passing through each fuel channel, air was blown through the gas circuits by the blowers and the flow measured by anemometers placed at the top of the fuel channels and recorded electronically. Next, the fuel charge and discharge equipment and the machinery for the disposal of spent fuel elements were thoroughly tested. As the reactor will be both charged and discharged on load, the charge face equipment being tested here is heavily shielded with lead. 13 fuel elements are mounted vertically in the body of the machine, ready for loading. There are fans at the top for cooling used fuel elements before they go down the discharge shaft to the cooling pond tunnel. The fuel chute enables the fuel elements to be lowered into or removed from the graphite core. After it's removed from the core, the spent fuel is delivered down the discharge shaft to the cooling pond 100 feet below. At the bottom of the shaft, the fuel elements are lowered by remote control into a lead-lined flask. Progress is watched by television. The machines they're testing now will take over when the reactor is on load. The flask is winched along the tunnel on bogies. The heavily shielded container automatically closes as it starts its journey to the cooling pond. At the other end of the tunnel, the flask is raised by crane to the pond above. In the cooling pond, the spent fuel is lowered into a numbered bin and moved along rails underwater to its allotted storage position. There it will remain for the necessary decay period, usually 100 days. The reactor was now fully charged with carbon dioxide gas for the first time, filling the pressure circuits ready for raising power. The gas is being tested here on arrival before transferring it to the CO2 store on the site. In the turbine hall, the turbo alternators and condensers have been steam tested. In the River Severn, the culvert gates at the outfall have been opened to test the cooling water system. With all the intricate mechanisms and machinery tested and proved, preparations now continue day and night for the final phase, placing 42,275 fuel elements in the graphite core. In August 1961, the Minister of Power granted approval for the loading of reactor number 1 up to critical size. The fuel, in sealed metal containers, was carried from the fuel store by forklift truck to the reactor building and taken up to the 4th floor. On the 4th floor, the elements, carefully wrapped in polythene, were removed from their metal containers and sent up to the fuel preparation room on the 6th floor for inspection. At the inspection bay, after scrutiny, the fuel elements were taken by carrier, 9 at a time, to the charge face for loading. For speed, the initial mass loading was done by hand inside the reactor. By hand, because it would be quicker on this one occasion than with the selective charge machinery. Once the core is irradiated, of course, it will not be possible to work inside the reactor again. In a few moments, the first reactor will be started up for the first time. The beginning of power output. Power from Berkeley. Nuclear power to the national grid. The blowers are started up. The control rods are slowly raised. Builds up. Steam pressure increases. Now steam is on its way to the dump condenser. Steam is passed on to the turbine. The turbine gathers speed. All set now to join the grid. The turbine is synchronized with the grid. Berkeley is on power. Berkeley is the successful climax to 5 years of construction, made possible by the skill of AEI John Thompson scientists and engineers, by exceptional manufacturing resources, and by the able cooperation of all who have contributed to this pioneer achievement.